An active low decoder uses external enabling signal of 0, which means the active enabling signal is going to be low. It will have the value of 0. An active low decoder is implemented using NAND gates, and the same like with the active high decoder, we're going to make a quick revision on the digital signal. A digital signal which has a value of 0 is treated as a low signal. A digital signal which has a value of 5 volts is treated as a high signal. So keeping in mind that we're using the same S0 and S1 as inputs, and respectively Q0, Q1, Q2, and Q3 as outputs, we will have to be very careful to note on our truth table and respectively on our diagram that the active enabling signal is being 0, which in reality means that everything, the whole logic of what we've been doing with the active low decoder is going to be inverted. With this on mind, we have already built a truth table. The truth table clearly shows that when the enabling signal is 1, then the S1 and S0 inputs are going to be our don't care, and the respective outputs Q0, Q1, Q2, and Q3 are going to have the values of 1. So the value of enabling signal being 1 actually says that our low decoder, active low decoder, is not being activated, and the outputs are going to have high values. Now what will activate the active low decoder are enabling signal values of zeros, and that's why we're having on all the following rows below 0 for enabling signal. They reflect the possible combinations for S0 and S1 and produce on our main diagonal on the output part of the matrix all zeros. So once we are moving from here to the logical presentation of the decoder, we have to consider that inversion of the input signal and respectively a proper inversion on the output signals is going to be applied. As you can see, 0 being our active low signal, enabling signal, we're going to have an inverter for the EN, and we're going to locate inverter for Q0, Q1, Q2, and Q3. Respectively, the logic of the implementation of the truth table is going to be inverted. So if we stay to our classic solution, which we had for the active high decoder, in here drawn in written in black, so here is the part which responds to the active high decoder. In order to make it work for the active low decoder, we will have to invert it. Applying Boolean algebra identities, we end up on summation of the respectively internally inverted multiplication signals. As a result, we can end up on a graphical presentation of a decoder which is implemented in reality with what we call NAND gates. Now, the most important part in here that the NAND gate being activated or using the inverse signal, low signals, is actually using the max terms, which is opposite to the active high decoder. Here we have a comparison between the active high and active low decoder in order to see the difference once we apply the inverter. So in the upper case, when we have active high decoder, one more time, we're implementing it using AND gates, and in the second case, when we're using active low decoder, we're implementing it using NAND gates. And one last reminder for the digital signal. It is treated as a low signal if it has a voltage value of 0, and it is treated as a high signal if it has a voltage value of 5 volts.